See, I have an automatic laser pointer.
Okay, so I'm going to sort of take some of the things that John has said and try and extend those to how we can use the GPU to calculate non-bonded forces. So I'm going to introduce by sort of contrasting against the electrostatic potential map calculation problem, and then I'll talk about the short-range non-bonded forces, and then I'll talk about some of our efforts to also apply the GPU to a method for calculating long-range electrostatics. So the particle-particle algorithms are more difficult. First of all, because we have irregularity in the problem, but also we have less fine-grained parallelism. In the last class of algorithms, we were talking about n particles, m grid points, but m here was somewhere on the order of 1 to 2 orders of magnitude bigger than n. And so when comparing the amount of work that we have, we see that the amount of fine-grained parallelism is reduced by like a factor of 20 to 200. Also, the particle-particle interactions require more data per interaction. So, can we use some of these optimizations like this loop unrolling to reuse data? And the short answer here is probably not, because we're going to have a lot more things here that we're going to be trying to hold in registers, and so if we're trying to do k of these with one thread, then our register use will explode there with k. We also, so you're probably familiar with the potential functions that we use for molecular dynamics, but for completeness I'm putting them here. We'll have more computational work here to do, so that's kind of the trade-off. We're keeping more data around, but we also have more computational work that we can balance the data movement with. So let's talk about some design issues for the short-range non-bonded force kernels. Well, it's a given that we'll want to calculate both the electrostatics and van der Waals interactions. And we'll need the atom coordinates, but we'll also need the parameters. We're going to have to be keeping forces as well. So spatial hashing of atoms into bins, we'll need this to make a linear algorithm. But this is best done on the CPU, probably. Should we use parallels? Well, the trade-off with using parallels is that although it reduces computation, it also increases and delocalizes the memory access. Should we make use of Newton's third law to reduce work? Our past efforts to try and to use this have really increased work because it increases bookkeeping in the GPU kernels, and so we end up being better off by doing twice as much work.
You guys know what it means, right?
Huh. It's going backwards.
There we go.
So, we've got other questions then. How do we map the work to the GPU threads? Well, maybe we could think about choose a fine-grained work decomposition, where we assign threads to sum the forces on the atoms. Maybe the best fit here is to each thread takes on an atom. We could think about an extremely fine-grained decomposition, where maybe we just assign the threads to the pairwise interactions themselves. A related question is, how do we decompose the work into thread blocks? If we assign thread blocks to the bins that get the atoms in our spatial hashing algorithm, we end up getting a non-uniform work decomposition. We could make this. We could consider making this decomposition uniform by assigning the thread blocks to, say, entries of the force interaction matrix. Other questions that we need to think about: is single precision enough? Maybe we need double precision. Maybe we need to use the compensated summation technique to sum the forces more accurately. We didn't have to worry about non-bonded exclusions in the electrostatic potential map calculation. But here we need to exclude atoms that are covalently bonded to each other, or that have a chain of a couple of covalent bonds to each other. And so, well, the problem is that if we go ahead and just do all this work on the GPU and then try and subtract out the excluded interactions later, this turns out to produce a lot of cancellation of the result, and so that reduces accuracy to the point that the calculation's basically ruined. So maybe our choices here are just to detect and omit excluded pairs in our GPU kernel. Maybe we can sort of ignore them up to a point, but use force clamping so that we don't let these forces, or maybe we do a force clamping on F over R. So maybe we pick a nice value where we don't let that get too large, and then we have something that we can go ahead and either subtract out later, or we can fix if add the rest of it back in if it should be there. So maybe we can use this technique to ignore the exclusion problem, but later fix it with the CPU.
And that's for the same issue. That's a floating point accuracy issue. You have destructive floating point cancellation if these would be very large numbers otherwise, and if you add that large number to what was otherwise a reasonable magnitude force, and then you try to subtract it off again, when you do that, you're basically destroying the floating point accuracy that you had from this cancellation. And so by clamping that force, you're going to prevent that kind of thing from happening, and then you can safely subtract it off. And that way you don't have to use either a very much larger precision floating point type or those other issues.
Also in some formulations of the short range part, we have some expensive functional form that has to be evaluated. For instance, the particle mesh AWOLT method requires the evaluation of IRF-C. So then the question, is it faster to use an interpolation table? But the trade-off here is if we go ahead and start doing table lookups, we become memory-bound rather than compute-bound.
Just to give you an example, on the CPU, an IRF-C call can take thousands of clock cycles for one call. And so the existing versions of NAMD on the CPU avoid doing that function call, and they use a table lookup technique. Because on the CPU, we're much more arithmetic bound than we are on the GPU. But on the GPU, this is probably not the right choice because, as Dave mentions, if we do a table lookup that's just adding yet another memory reference, and we have many of them already, and that may be making our kernel bandwidth bound, and that's exactly what we don't want to do because we want to get a speed up greater than 10. If we end up being memory bandwidth bound, then we're best case likely to hit a performance that's only 10 times faster than the CPU.
Right. So just a preview here. The earliest GPU kernels that Jim developed for NAMD, so that we didn't have to pay the penalty of calculating this in the GPU, because the early GPU models you didn't have any kind of acceleration for or hardware implementation for IRFC. He went ahead and successfully used an interpolation table and had a nice, clever design that made nice use of the texture unit. However, Fermis now have hardware support for an IRFC function. Also, when I talk about an alternative in-body solver to PME, this multi-level summation method that I work on, that's something that has a splitting that doesn't rely on IRFC. So there could be some advantages there. We have a splitting where we just have we split using a polynomial, and so we just have multiply adds, which are very GPU friendly. So this slide shows depicts the NAMD decomposition. So NAMD does a spatial decomposition, a 3D spatial decomposition, but it doesn't stop there. To be able to use a lot of parallelism and big supercomputers on relatively small input sizes, there's also a decomposition of the computational work that's done. So here we call